Good morning, everybody. Today we are going to look at mostly review material, but some of the, new versions of what we've already learned already. So you already have this in front of you, or if you don't, it is on our website, those of you at home. And we're going to talk pretty much today about restriction enzymes and what is ultimately known as a plasmid map. And we'll talk about how we can put all of those things together and also review gel electrophoresis and how to run it and how to map it out. So by the time we're done with this video, and it'll be posted on our site, if you want to watch it again, you'll be able to do about 3 or 4 skills from this chapter. So we talked a little bit about restriction enzymes, and we call them restriction endonucleases. And basically what we said they had the ability to do was cut very, 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 very specific places in a DNA molecule, and they're going to break that phosphodiester bond or that covalent bond. They do not get involved in the hydrogen bonds. That's going to just happen as they get broken apart, but they are specific to the phosphodiester covalent bonds in between nucleotides. Once again, I cannot emphasize the specific nature of these enzymes and how important that is. And ultimately what will happen is they're going to allow you or scientists to cut DNA in specific places and then take genes from one organism and insert them into another. And we're going to talk about that as recombinant DNA, or taking information from one organism and placing it into another. And restriction enzymes were discovered because they are involved in bacteria trying to chop up viral DNA. So if you look in this picture here, this is called the bacteriophage, and that blue area inside the orange capsid there is DNA, and what will happen is it will be injected into the bacteria, and of course the bacteria don't want that, so it is the restriction enzymes that come in and take care of this viral DNA, and sometimes it works and sometimes it doesn't. And we'll see how that is what allows scientists to find these very, very, very specific regions and cut them in a very specific order. So what are we looking for here? Well, we're looking for these things called palindromes. And what they are sections of DNA where they're identical in both directions. So, for example, if you look at the top, it goes GAATTC. And if you come back on the bottom in the opposite side, it's GAATTC. So they're exactly the same. And what's going to happen is the restriction enzymes are going to be looking for these exact specific places called restriction sites. And they're anywhere from 4 to 6 base pairs in sequence length. And you'll see a few examples. And there are many, 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 many restriction enzymes. And in the event that you are given one, you will not be expected to know exactly where it finds and where it cuts, but there'll be some background information provided. Once you know that, then you'll be able to answer the question. So let's take a look first at HAE3, and I'll get into how they named these restriction enzymes in a second. But this particular enzyme is going to look for the pattern of 2 G's and 2 C's in a row. So if you look here and you move along and it doesn't happen, and finally it does. And there's 2 G's in a row and 2 C's, and of course coming backwards there are 2 G's and 2 C's in a row right there. And once it finds it, it's going to make a very specific cut right in between the G's and the C's. So in essence, what you're going to end up with, if that was only cut one time, let's say that it was an example that was cut only once, you're going to have one cut, which would be right there, one cut, and it's going to give you a total of 2 pieces. One piece over here, and then the second piece over there. And obviously there's DNA going in both directions. I don't want you to think it's that small. When the restriction enzyme makes a clean cut, that clean cut is known as a blunt end, or you can see that there's no hanging edge, there's no what we're going to call sticky ends in a minute. It's just a clean cut. And that's great if you're looking to make a specifically clean cut in a piece of DNA. So you would use that very specific, that particular restriction enzyme. But scientists, well, they want to get a little bit more fancy. So they may use HIND3. Now, HIND3 is also a restriction enzyme that's going to look for a very, 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 very specific section of DNA. In this case, it's looking for AAGCTT, this section right here. And once again, here it is coming back on the bottom strand, so everything's cool. Now, in this case, it's going to make the specific cut in between the two A's. Now, by doing that, you're going to see that the two cuts are uneven, and that's actually good for recombinant DNA, which scientists are going to look at. And what you have to remember is that in between here, there are hydrogen bonds. Now, what's going to happen, and we learned that from all of the nucleotides and DNA and RNA and all that we did. So once that covalent bond is cut in between those two A's, now the DNA can be separated. And what's going to happen is right in this area, that's where you're going to break those hydrogen bonds. So those H bonds are now broken. And once they're broken, you can separate the two strands of DNA. Remember that DNA, or these nucleotides with these hydrogen bonds, are very much like magnets. So with this AGCT kind of hanging out and this TCGA kind of hanging out, they really want to go back with their buddies. They really want to match back up, and that would make them happy. And scientists are counting on that. So that's why you can take, let's say that this is a gene, let's just say on this side, you can take this entire section, this now gene that you cut, and place it into a new organism, because when you do, assuming you use the same restriction enzyme, you're going to have these same sticky ends, and the DNA is going to be very happy when it finds its, in essence, buddy in the new organism. So, quick review: blunt ends are clean cuts. Sticky ends are going to have this, almost these tail pieces that stick off, which will make it very good for scientists to take some DNA from one organism and, in essence, insert it into a different organism. And we'll see that coming up in a little bit. So where do these restriction enzymes get their name? Well, they're going to get their name from the type of strain they are, from the name of the bacteria they are, and when they were discovered. So, for example, EcoR1 comes from the Escherichia coli. Again, funny name, E. coli we call it. And it's the R strain, so that's the R. And then the one was the first one to be discovered, so EcoR1. And some of these might have a 3 or a 2, and it all depends on when they were discovered. So EcoR1 came from the E. coli bacteria, R strain, and it was discovered first. So if you look at EcoR1, well, what's EcoR1 looking for? Very specific bases. What about BAMH1? Well, let's see. What's BAMH? Oops, like this. What's BAMH1? Come on. What is BAMH1 looking for? Well, there's your restriction enzyme. This is looking for GGATCC, where it makes its cuts in between those two G's. This will produce what are known, again, as sticky ends. Very good for scientists. But ALU1, that is not going to make sticky ends. That's going to look for AGCT, and AGCT going that way, AGCT going that way. And it's going to cut between the G and the C, and since it's a clean cut, that would be known as a blunt end. So those, again, are specific examples, and there are lots and lots of them. So please don't think you have to memorize them, because you do not, but know that there are many, and they are very, very, very specific. So what's the goal here? What are scientists looking to do? They're looking to take specific DNA or specific genes from one organism and then, in essence, splice it into another one. So if you look at this picture here, you can see that there are restriction enzymes that are needed to break the DNA, and then there are restriction, and then you have to do the restriction enzyme in both. And you can see that these little bits, these little pieces of the specific genes have been inserted into that new plasmid. Fascinating, fascinating, fascinating. And I showed you the other day before you left that what we can do for humans is we can take the specific gene, let's say this gene here for insulin, we take this out of the human genome. And the reason why we can do this is because the A's, the T's, the G's, and the C's between bacteria and humans, that it's all the same. They're all nucleotides, so you're not reinventing anything. So you specifically cut out this target gene. You then specifically open a plasmid in a specific place. You then insert it into that plasmid, and if you notice, here are your sticky ends, and the sticky ends are very likely to join up with the hydrogen bonds. Then you have to bring in DNA ligase, and that's going to seal up the deal. That's going to recreate that covalent bond between those nucleotides. And now you have this, what's known as a recombinant plasmid. And bacteria, as you know, replicate very fast, and you can make many copies of this very, very, very quickly. And then through various preps and through various kinds of filters and many more scientific steps than you'll need here for this part, the scientists can, in essence, get out just the insulin that was made from that specific gene in bacteria, which is crazy, 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 crazy. Now, what are we going to do with that here? So that's an easy piece of knowledge, and okay, you cut it out, you put it in, whatever. But if you want to kind of quantify that, and you want to put some numbers to that, you're going to do these things called a plasmid map. And the best way to kind of model a plasmid map is by using a clock. Now, this particular clock, let's assume it has 12 hours, let's just say, and let's just say that each hour on the clock represents a total of 1,000 base pairs. This plasmid would have a total of 12,000 base pairs. And if you believe that, then that is phenomenal, and I'll show you how it works in a second. Usually what they'll do is they'll give you a restriction enzyme, and they will tell you the specific place where it is going to cut in the plasmid, and then you'll practice that coming up when we're all done here. So let's look at this clock, and let's look at what they gave us. They gave us some clues here. The first restriction enzyme was EcoR1, which you know about. And again, you don't need to know the specifics on that, but here it's telling you it's making a cut at 1,000, which on our clock would be 1 o'clock right there. So if you want to kind of keep things straight, you can put your restriction enzyme on the place of the cut and check it off. EAG1, that's going to cut at the 5,000th base pair place. And again, if you want to just label that, you can. And then APA1 is going to cut at the 9,000 mark, which would be right there. And now you have made a total of 3 cuts. And that's going to give you, on a plasmid, 3 pieces in this case. So you have 3 pieces. And if you were to count them up, you know that every hour is 1,000. So that would be 1,000, 2,000, 3,000, 4,000. You know that this particular piece is 4,000 base pairs long. 5 to 9, this piece is also 4,000 base pairs long. And from 9 all the way over to 1 is also 4,000 base pairs long. So if you were to add up 4,000 plus 4,000 plus 4,000, there's your total of 12,000. And that is a really good way to double check what you have done and make sure you didn't make any math errors. This is a simple one. So in our first example, how long is each piece? Well, each piece is 4,000 base pairs in length. They're obviously not going to be that easy, but I like to give you kind of a break at first. So let's see a little bit more obnoxious example. Same clock. Nothing's changing. Everything's cool. Same rules. Every hour represents 1,000 base pairs, so we're not changing anything. And on a sample question, which I will give you, they'll tell you how long the plasmid is. You don't have to guess. So on this one, let's make our first cut. Eco R1 is going to cut at 2200. So 2200 is going to be right there. And we know that because each hour represents 1,000. And let's just put an EC for that one because I kind of ran out of paper on that side. EAG1 is going to cut at 5,800. So let's put EAG right there, 5,800. APA1 at 9,400 right there. And then finally HIND3 at 11,200. So in the event that you were given these 4 specific restriction enzymes and they cut at the specific place as given, we can answer some questions. How many cuts were made? Pretty easy. 4. Once again, this is circular DNA, so how many pieces do you have? 4. All right, that's cool. But now, how big is each one? And the general rule of thumb is, and in the activity that you're going to do when we're done, is put them in most to least order because that's how it's going to be run in the gel. So if we do our math real quick, we're going to see that this piece up here is 3,000 base pairs long. Oops, base pairs. Okay, we add that up. This one over here is going to be 3,600 base pairs, that next piece. This piece is also going to be 3,600 base pairs long. And finally, the smallest piece up there is going to be 1,800 base pairs. And in the event that you were kind of scared on your math, you add up all 4 of those numbers, you will get 12,000 because that is how long this particular plasmid is. So in putting them in, again, decreasing order, you're going to have a piece that's 3,600. And it's okay that you have 2 here in this case because you do. They just happen to be exactly the same. Now in real life, that's probably not going to happen, but it did here. Then you have a piece that's 3,000. And finally, you have a piece that's 1,800. Now, when you run your gel, which we'll do in one of our practices that we have coming up, you can draw the bands wherever they're going to be created. And again, I'll show you that example in a little bit. So as for the generalizations, I guess, of restriction enzymes and these plasmid maps, hopefully that was helpful. Now, how can you apply all of that? Because now, let's get down to it. We got to, what do we got to do with it? So if you look on the last page, this is kind of a very, very, very simple example. But they gave you a piece of, well, I guess we'll call it DNA, and the total piece is 42 base pairs long in this case. Well, let's see. I have 2 restriction enzymes. So let's focus on each restriction enzyme by itself, and then we'll do the whole total. So if this was a piece that was 42 base pairs long and Eco R1 came in, Eco R1 in this case was going to make a cut at 10 and was going to make a cut at 28. So in doing that, you'll be able to add up how big each of the pieces are. So from 0 to 10, that piece is going to be 10 base pairs long. From 10 to 18, 10 to 28 is going to be 18 base pairs long. And then from 28 to 42 is going to be 14 base pairs long. And if you add up 18 plus 14 plus 10, you'll get 42. And that's what you always want to double check. So let's say that you cut those, you did that PCR we talked about, you made a lot of copies of each of those little fragments, and you ran it. Let's focus on the Eco R1 gel right here. Well, I should have a piece that's 18. There it is. I should have a piece that's 14. There it is. And I should have a piece that's 10. There it is. Once again, biggest to smallest. In reality, it's not 18 and 14 and 10. It's in thousands. So this KB represents thousands. So it's bigger than 10, 18, and 14, but for simplicity. Well, what if I did not use Eco R1? So I get rid of all that. What if I used XBA L1? All right. Well, this makes 3 cuts. How big is each cut? I don't know. This piece is 6. This piece is 12. This piece is 20, and this piece is 4. If we ran the gel, let's see if it worked. 20 is right there. 12 is right there. 6 is right there. And 4 is right there. Okay, fine. Then, of course, they're going to try to trick you, because that's what they do. And they're going to say, all right, what if I give you a piece of plasmid, and I give you 2 restriction enzymes? Well, now we got an interesting problem here. Well, let's see what happens. My first cut is from 0 to 6, so this represents a piece that's 6. Now I go from 6 to 10, that piece is 4. I go from 10 to 18, that piece is 8. 18 to 28 is 10. 28 to 38 is also 10. And then 38 to 42 is 4. So now my pieces are 4, 6, 8, and 10. I run my gel. Let's see what happens. Here's my gel with both of them right there at the top. And voila, 10, 8, 6, and 4. Obviously, the more restriction enzymes you put in, the more pieces you will get, and the smaller the pieces will get. And this is a skill that if you can apply it, you can draw out these various gels if they give you paper, or you can analyze them from the tools given to you. So I thought that was a pretty interesting kind of simplistic way to look at it. So let's look at something that's going to be a little bit more detailed. Now let's see what we got here. So this here is I guess we'll call it a lab for lack of a better term. It's not really a lab, but if you can get to that website on your phone, you'll be able to watch a brief, it's, 6 or 8 little kind of simple animations that walk through the process of gel electrophoresis. If you can do it in school, that's great. If you can't do it in school, just do it at home. It'll take you, 5 minutes or so. And you may know the answers to these questions without even looking up through that little animation. If you happen to know the answer to some of these questions without the animation, that's great. Go ahead and answer them. If you don't know the answers, watch the animation. Either try at school, I know that the reception is not too good, or go home tonight and do it. Like I said, it's going to take you less than 10 minutes. It's very, very, very simple. And some of these things are very detail-oriented and very obnoxious, and you're not going to need them for real life, but I just wanted to give you a little background on gel. And we kind of talked about it in class already, so it's not, these super specific, annoying details. It's not something you're ever going to see, but it's good to know. But this is something that you may get. So the question here is circle the smallest fragment, circle the largest fragment. If we know that this is gel, which it is, and we know that that's the well, so the well is where we always start. And we remember the rules, smallest goes farthest, the biggest stays back. So it's going to be pretty hard to draw in here, but that is your, if you can see it, smallest. Oh, it is purple, you can see it. And this piece will be your largest, and we talked a lot about the smaller the pieces, the further they move down the gel. And then this thing was your ladder, and that will allow you to determine how big each piece is. This, of course, is going to do you no good because the ladder is not labeled, but in what we practice, it will be. So this here, one of the things I always like to do is kind of make sure you know what you're doing instead of just leave you out to dry and then having kids with question marks over their head and getting ready to curse me out. And I don't want to do that. So I'm going to show you how to do this with one example, and then you'll do the rest. So in this particular assignment, I gave you a plasmid, and this plasmid is 48,502 base pairs in length. So that's important to know. You have to know how big you're dealing with your original plasmid. Then I gave you several restriction enzymes and where they made their cuts. So there's a lot of choices. So let's pretend that we do them individually. We're not going to do them all together because forget it, your hair will fall out and you look worse than I do. So let's do the Eco R1 together. So if you look at the Eco R1, you can see that there was several cuts made in the plasmid or the DNA. And let's kind of fill in what we know. We know that this end is, we know that this end is 0. So let's go ahead and pencil in a 0. And we know that this end is 48,502 base pairs. So that's the total length. Where it made these specific cuts at these specific base pair numbers. So now you just use a calculator. A regular calculator is all you need. So you're going to determine the size of each piece. So this piece is going to be 21,226 because that's easy. 21,226 minus 0 is 21,226, obviously. Then you're going to use your calculator to determine how big each piece is. So this piece is going to be 4878 base pairs, 5643 base pairs, 7421 base pairs. And I would suggest doing it this way. It will make your life a lot easier. 5804 base pairs. And then finally, this little piece is 3530. So if you add all those numbers up, they will equal 48,502. So that works. We like that. And from here now, you can make I guess we'll call it a fake gel, if that's a way to say it. So you wrote down all these pieces, and then you're going to come to this chart on the next page, and you're going to, in essence, make a map. You're going to be making a gel. And you will do it from largest to smallest, just like it would run in real gel. So in the Eco R1, our largest piece was 21,226. So write that there, 21,226. Then our next largest piece was 7421. Our next largest piece was 5804. Our next largest piece was 5643. Then we had 4878. And then finally we had 3530. So these are your pieces according to that strip of DNA, that piece of DNA. And if you were to model what the gel would look like, you would simply go to your gel. And of course, they have to give you a ladder, which they did. And we know our first piece is around 21,200. So that's going to be somewhere around here. And again, it doesn't have to be perfect as long as you're close. So there's your first band, a little bit more than 20,000. Then our second band is somewhere around 7,400, which again is hard to do here. So it's going to be somewhere around here. And again, do your best. About 7,400 right there. Then we have about 5,800. Now, you know the 7,400, let's move that. That might be a little bit higher. 7,400, maybe it's up here somewhere. And I would use a pencil if I were you. Then we have a 5,800 and a 5,600. And again, they're going to be tough to draw because they're so close to each other. But again, do your best. Then you have a 4878, which is just a little bit smaller than the 5,000, which would be somewhere around there. And then finally, you have a 3530, which again will be somewhere around, I don't know, maybe here somewhere. And again, it's tough on this ladder because you can see that this gap here is worth 20,000, and this gap here is worth 2,500. So, you know, unless you're a meticulous artist with a tighter scale, you're going to have a rough time. But as long as you can generalize and you can be close with your pieces, then I'll be happy that you know what you're talking about with this. So that is that portion. And then the last part of this is the very first set of notes that I gave you. Now there might still be one little typo in this, and I'll show you where that little typo is. But this was your homework for the other day, just to kind of fill these questions out. But it should be pretty easy now that we've talked about all this. Then, if I give you a bunch of restriction enzymes and tell you where to cut them, could you recreate the cut sequence? Could you tell me if it's sticky or blunt? And could you tell me if we would use it for recombinant DNA or not? And the answer to that is yes. In the event that some of you, and I don't know how the copies came out because we had a little bit of a typing issue, but if the top strain is right, so if the top strain, let's say, is GGATCC, but for whatever reason, if your bottom strain doesn't work out right, for whatever reason, if I know there was a typo somewhere, and I know we made the correction, but I think I missed one, just fix it so that it works, obviously. And let's do the top one so you can see what I'm talking about. And if you can do this, you're set to go. Top one, cut sequence is going to be G, then I'm going to leave a space, and then I'm going to have my A, T, T, C, and that space is where the cut is. Then over here I'm going to have G with the space, then I'm going to have my A, T, T, C. So I know it was not a clean cut down the middle, so this is going to be a sticky end. That's how I know what kind of cut I have. And we said that sticky ends are good. Could you use it for recombinant DNA? Could you use it to insert genes from one organism to the other? That answer will be yes. So now that you know that base, you know what the cuts are, how the cuts work, what it means, you can fill in the rest of this chart. Then there's a little example right here with some questions which you will be able to work on as well. And then finally, I'm going to leave you to this one. I'm going to see if you can figure this one out. This here is a plasmid, and there's a bunch of different restriction enzymes making cuts all over the place. See if you can figure out, with all the knowledge that you've just learned from me over the last couple of days and in this video, if you can figure out how to answer these 4 questions based on that particular picture. And if you can, you're all set. So work on that for the remainder of this period and into next period if you need it. If you get done with everything, you can take a large piece of paper if you want to work on that extra credit, which is over on that side piece over there, a little bit above Victoria's head, and she can get it for you. Or over by Sahara, over there somewhere. And if you put on one side a beautifully drawn and colored in DNA replication, and on the other side beautifully drawn and colored in and labeled protein synthesis, if you want extra credit on your test. Then also I posted, or I sent out to you the instructions on the review book, how to start that for the rest of the year. We'll be doing that pretty much every week for the remainder up until the test. And by the time you're done, you're going to have a beautifully built, laid out review book. I started mine already. I'll bring it in. I'll show you on Tuesday. And if you happen to have access to the internet, or you printed it out or whatever, and you want to kind of look at the first page of that or two, whatever, feel free to do that. So with that, you have all the instructions that you need, and do your best. And I will see you all on Tuesday. Have a good day.